Midweek last week, we started talking about a concept called work. We defined work last week as the change in energy experienced by something, the energy that's gained or lost by something. And we abbreviate that often just with a simple little equation, W is equal to delta E. That's actually called the work energy theorem, what I have written up on the board right now. The definition of work is the work energy theorem. W is equal to delta E. But work is also equal to, in addition to delta E, it's also equal to F times D, or sometimes, in fact, F times D times cos theta. Can you tell me the difference? When is it equal to F times D? And when is it equal to F times D times cos theta? When do I get to drop the cos theta? When do I have to include the cos theta there? Yeah, Julia? What angle, though? Okay, so what does theta represent? An angle, but what angle? The angle of the sun above the earth? Okay, so it's the angle of the force relative to the angle that it moves at, right? So if I push it at 30 degrees and it moves at 0, then the angle that I would include would be 30. If I push it at 45 and it moves at 30, then the angle that I would be concerned with, theta, would be 15 degrees in that case. If I push it at 175 and it moves at 175, then the angle would be 0 in that case. Theta is the angle between the way that I push it and the way that it moves. Now, usually that angle is what? In most cases, when we're doing a problem, theta is going to be equal to 0. It means the way that I push it is the way that I move it. When I set theta equal to 0, then cos theta becomes equal to 1, and F times D times 1 simply becomes F times D. So in other words, if you're pushing it in a certain direction and it moves in that direction, then let's say theta is equal to 0. Let's just drop the whole cos theta entirely and make it F times D. If there is an angle, okay, then I want you to take a look at what that angle means. Is it the angle between the way that it moves and the way that it's pushed? Or is it some other angle? If it is the angle between the way that it moves and the way that it's pushed, then we're going to tack on the cos theta on the end of it, and W becomes equal to F times D times cos theta. All the while, remember, either one of these can be equal to delta E, the work energy theorem, the change in energy. Then we took a look at power. Okay, the concept of power. And we said power was a rate, specifically the rate at which work is done. So it's real closely related to work, but it's not work. It's how quickly the work is done. Now, velocity was the rate of change of position. So in other words, it had change in position over time. Acceleration was the rate of change of velocity. So it had time on the bottom and change in velocity on the top. Anything that's a rate has time on the bottom. Therefore, power will be equal to something with time on the bottom. What's on the top? The rate at which work is done. What's on the top? Work. So power is equal to W over T. Now, in a sense, a completely new topic from work, right? Because power is different than work. Just like velocity is different than displacement. But the reality is when you see a power problem, it usually ends up being a work problem, which you have to divide by T. So basically I'm saying when you see this power problem, I want you to solve it as a work problem, get W the same way as you would if you were solving for W, and then just simply divide it by the time that you have. Now we did an example. Our sample problem was just kind of a little mini activity where I had you guys run up the stairs or walk up the stairs and find the power output of your legs. We calculated the power output of your legs by saying W over T. We measure the time, easily measure the time with your phones. 2.4 seconds, 3.9 seconds, whatever the case may be, how long it took you to go up those stairs. We found work, the work that it took you, the work that had to be done to go up those stairs as well. We know that work is equal to F times D, but we didn't know the force that you applied parallel to the displacement that you walked or ran. So we didn't use that. We ended up using the whole idea of the work energy theorem, delta E. And we said the final energy was potential, and the initial energy at the bottom was 0. So basically we said the power, your power output, the power output of your legs when you climbed those stairs was equal to mgh, final, which is your final potential energy, a change in energy that you experienced running up those stairs divided by the time. And we found ranges, I think, anywhere from about 200 watts or 200 joules per second up to, what was our highest? 900 or something like that? Okay. The person with the power of a horse and the person with the power of a puppy dog or something. I don't know. I don't know what has the power of 200 watts, but not a horse, anyways. Guys, we okay with that? All right. We had 5 questions on our power worksheet, the energy worksheet number 4. I'd like to take a look at, let's take a look at all 5 of those questions, actually. They'll go pretty quickly for us, so we'll do all 5. First question says, if the time over which energy is used up increases, what happens to the overall power? If the time over which the energy is used up increases, if T goes up, and assuming W stays the same, if T goes up, what happens to power? Yep. Sorry. Yeah. If the number on the bottom goes up, then the number that you're solving for is going to go down, and vice versa, right? Okay, we talked about that with our little example at the beginning of class when we introduced this concept. I can't remember who was that we had used as examples, but basically we said, look, 2 people shovel the snow to driveways, both identical driveways, both the same amount of snow. They both do the same amount of work, but one person takes 3 hours, one person takes 1 hour. I think Jared was the one that took 3 hours, wasn't he? Same amount of work, right? Just means that Jared's power was less because he took more time. T is bigger, power is smaller. T is smaller, power is bigger. All right, question 2. 2 says the energy a man expends lifting a box is 500 joules. Takes him 2 seconds to lift the box. What's his power output? Pretty straightforward question. The energy expended is 500 joules. That's the change in energy. And change of energy is equal to work. So we're just simply going to say the work is 500 joules divided by a time of 2 seconds. That's going to give me 250 joules per second or 250 watts. How much energy is used by a 1500 watt hairdryer if it's left on for 6 minutes? Well, once again, power is going to work over time. We're looking for the energy used up, but the energy used up is delta E, right? Which is, by definition, equal to W. So really what we're solving for here is W, because power times time. The energy used up is the work done by the hairdryer. So we're going to say it's 1500 watts times a time of 6 minutes, although we want to convert that 6 minutes to seconds. So that's going to be, what, 360 seconds? How many digits should that be? 3 digits, 5.40 times 10 to the 5 joules. So that's, what, 540,000 joules, right? That's a lot of energy, right? Basically what I'm saying is don't turn your hairdryer on for 6 minutes, right? Because it uses 540,000 joules. You guys know how much electricity costs these days? Well, it costs about 10 cents per kilowatt hour. And a kilowatt hour is about 3.6 million joules. So you're using 540,000 joules of electrical energy as you leave your hairdryer on for 6 minutes. 540,000 joules, 3.6 million joules costs about 10 cents. So what are you using here? About 1/7. You're using, I don't know, about 1.5 cents worth of electricity when you leave your hairdryer on for 6 minutes. Hey, that adds up though. 1.5 cents times 30, 45 cents a month it takes you to keep your hair dry. So watch out. 4 says an 1100 microwave oven means an 1100 watt microwave oven. It's turned on for 2 minutes. What's the energy consumed by the microwave oven? Once again, power is equal to work over time. The energy consumed is delta E, which is equal to W by definition. So we're solving for W here. Power times time. The power here is 1100 watts, or 1100 joules per second. We turn it on for 2 minutes. 2 minutes is 120 seconds. Multiply those two numbers together. So we get 1.32 times 10 to the 5 joules. Boy, turn on your hair dryer in the morning for 6 minutes. Then run downstairs and turn on the microwave for 2 minutes to cook your bacon. And you've just spent, well, you've probably spent over 2 cents this morning already by doing that. Sorry, no, you haven't. Your parents have just spent over 2 cents as you're wasting their money like that. 5 says a 2 kilogram box is pushed 20 meters with a force of 50 newtons. Takes 8.5 seconds for the person to push the box this far. What's the person's power output? Okay, power is equal to work over time. But remember, okay, when we're encountering these slightly more difficult problems, treat it as a work problem first. Okay, guy pushes the box 20 meters with a force of 50 newtons. We can find the work. Work is equal to F times D. Now, we're going to assume that he pushes it the way that it moves. So we're not going to worry about the cos theta there. It becomes 50 newtons times 20 meters. That gives me 1,000 joules. That's our work done, which will turn around now 1,000 joules and divide it by the time of 8.50 seconds. What do we get when we do that? Thank you, Nathan. We get 117.647. I said joules. It should be watts, shouldn't it? And of course, we should round this. If we go back to our data in the question, we had 2.00, 20.0, 50.0, 8.50. Final answer should be how many digits? 3, which is 118 watts. You know what some people like to do here? 3 digits, 120 watts. Is that right? No. You look at the digit right after. You look at the 4th digit. Okay, if the 4th digit, you want to round it to 3 digits, look at the 4th digit. If the 4th digit is 5 or greater, then you round it up. But you don't round up the 2nd and the 3rd digit. You just round up the 3rd digit, the last digit, and it becomes 118 watts. Right? Last topic of the unit here now. Get us ready for our test coming up on Wednesday. The law of conservation of mechanical energy. What do we mean by mechanical energy, first of all? Well, mechanical energy is just the sum of kinetic and potential energy. Okay, we've been talking about mechanical energy this whole time since we introduced the concept of energy. The kinetic energy of the car as it rolls down the hill. The gravitational potential energy of the car as it rolls down the hill. The sum of those two is mechanical energy. The kinetic energy of the elastic when I let it go, combined with the potential energy of the elastic that it still has, that's mechanical energy. The sum of kinetic and potential energy is mechanical energy. Now, the law of conservation of mechanical energy says this. Energy can't be created and it can't be destroyed. You can transform it from one type to the other. In fact, sometimes when you transform it, it appears as if it is created or destroyed. I flip on the light switch and my light comes on. Where did the energy come from? It looks like it was created from nothing. It wasn't. 80% of it was created or was transformed from chemical potential energy into electrical energy when we burned coal at some coal-fired power plant somewhere. It wasn't created. It was transformed from chemical potential to electrical energy. Maybe a slam on the brakes of the car. You come to a stop. You had kinetic energy, and now you've got no energy. It looks like energy was destroyed. It wasn't. It was just transformed from kinetic energy of the car into what kind of energy? What kind of energy was it transformed to? The car's at rest. It's not moving. It doesn't have a height. It was transformed into, most of it was thermal energy. You probably heard the car stopping as well. So a little bit of sound energy, but most of it would have been heat energy. Again, energy is not created or destroyed ever. It is transformed from one type to the other, and sometimes that makes it look like it's created or destroyed, but it's not. Now, sometimes we add energy to a system because of wind, because we push something, because you put your foot on the gas pedal and chemical potential is converted to kinetic energy in the car. Sometimes we add energy to the system, but again, we're not creating it. We're just converting it from one type to the other. And similarly, sometimes energy is taken away, like the friction example of the car stopping that I was just talking about. Usually when that happens, it's transformed into thermal energy, but that's still a form of energy that ends up being dissipated in the air. You warm up the air a little bit. Not very much, but air resistance and so on. If we account for every joule of energy, whether it be an easily measurable kinetic energy or gravitational potential energy, or whether it be an energy that's a little bit more difficult to account for, like thermal energy that's produced when you slam your foot on the brakes, if we account for every joule of energy, then the total energy will always remain the same. You never gain, you never lose, if you account for everything. Does that make sense? That's pretty fundamental to the problems that we're going to do in a moment. We're going to say in the problems that we're going to do in a moment that the total energy remains the same. We're going to account for everything. Now, in order to simplify that a little bit, we're going to do problems where there is no energy added to the system. There is no wind that propels it forward, or there is no friction that takes energy away from the system. We could do it and account for those, but it would be more complicated. This year in Physics 20, we look at systems where there are no outside influences. There's no friction. There's no air resistance. There's nothing like that. If that's the case, then we will always say that whatever energy we start with, EI, will be the same as the energy that we finish with, EF. Initial energy equals final energy. The law of conservation of mechanical energy. Conservation means, we talk about conserving the environment. We keep it the same. Right? We don't make it worse. We don't destroy it. We keep it the same. We conserve energy. We keep it the same. If we keep it the same, then the initial energy must be equal to the final energy if we're accounting for everything. So what does this really mean? Where are we going to use this? Like what kind of situation does this become practical for us, other than knowing? There is something to be said for just knowing something for the sake of knowing something, but really in Physics 20, we're interested in where do we apply it? Okay, where does it come into everyday life or practical experience? Well, let's take a look at a car going down a hill, or for that matter, a roller coaster going down a hill, which you're all going to experience in your field trip in just over a month. Roller coaster cars going down the hill. Okay, it's got, what kind of energy does it have at the top of the hill? Let's assume, by the way, it's at rest at the top of the hill. Colleen, what kind of energy does it have when it's at rest at the top of the hill? Yeah, it's got gravitational potential energy. We're going to call this EI, by the way, because that's what kind it's got at the beginning. What kind does it have when it reaches the bottom of the hill? Okay, it's moving, right? So at the bottom of the hill, we're going to call it EF. It's got kinetic energy. What we're saying here with the law of conservation of energy is that EI equals EF. If we're accounting for everything, there's no friction here. Okay, there's no air resistance here. If we account for everything, then the initial potential energy that we have at the top is equal to the final kinetic energy we have at the bottom. You got a spring here that's compressed. Okay, I pull back that spring. Remember I told you guys one day about those clothespin guns that we used to make when we were kids? You pull back that elastic. It's stretched for, for 10 centimeters or whatever it's stretched by. Okay? And then you let it go. Okay? This is before, and then after is you let it go, and then the little clothespin thing that's on the end of it gets fired off like this. What kind of energy did we have at the beginning of this? When the elastic is pulled back or the spring is compressed, what kind do we have? Potential. The initial energy here would have been 1/2 kx squared potential, right? What kind do we have after it's released? Kinetic energy, right? Because it's moving. So the final energy would be equal to 1/2 mv squared. What are we saying here? Well, if we account for everything, then the law of conservation of energy tells me that EI is equal to EF, or in this case, 1/2 kx squared would be equal to 1/2 mvf squared. So this is where it comes into play, but what use is it for us? Well, we can determine how fast the car is moving at the bottom of the hill. That might be useful to know if you're designing a roller coaster. How fast is the car going to be moving when it reaches the bottom of the hill? We could figure out how fast the little clothespin, the clothespin spring is going to be moving when we fire it off. Okay, that may be a little less important when you're designing a clothespin gun than how fast you're moving at the bottom of a roller coaster when you're designing a roller coaster. But in the end, it's still something that sometimes we want to know. How fast is it moving when it's released? The EI is equal to EF. Here's what you got to do. Figure out what kind of energy you have at the start. Figure out what kind you have at the end. Set them equal to each other. Solve for what you're looking for. Simple as that. Okay, we got an example problem here. It says a 500-gram ball is thrown downward at a speed of 5 meters per second from a height of 35 meters. What's the speed of the ball as it hits the ground? You can do this the old-fashioned way. You could have done this a week and a half into school. I don't want you to do it that way. Okay, if on a test you did it that way, all right, I'd mark it right. But right now I want you to do it my way just so that you experience that. What kind of energy does this ball have before it's released? In other words, at the top, what kind of energy does it have? Yep. It's got potential energy because it's got a height of 35 meters, right? Is that it? Is that all it has? Why does it have potential energy? Because it's got a height. What other kind of energy could something have? Kinetic. When does it have kinetic energy? When it's moving. This has a height and it is moving at the beginning of the problem. Therefore, it's going to have kinetic and potential at the top. What kind of energy does it have at the bottom? When it reaches the ground at the end of the problem, what kind of energy does it have? Yep. It's just kinetic, right? At that point, it doesn't have any potential because it has no more potential to fall, so it's just kinetic. Now, which one is going to be greater, the kinetic at the top or the kinetic energy at the bottom? Right. And why is it going to be greater at the bottom than it is at the top? Right. The total energy is the same. But if you had kinetic and potential, if all your energy was split between the two types at the top, but all of it is kinetic at the bottom, then you must have lost potential, gained kinetic. So the conversion is potential to kinetic. You still had kinetic at the beginning, but now you've got more of it. Let's set it up. Let's set EI equal to EF, because that's the law of conservation of mechanical energy. EI equals EF. The energy at the top is kinetic energy, potential energy, and kinetic energy. The energy at the bottom is just kinetic energy. You guys did a little bit of this in Science 10, right? You might not have called it the law of conservation of energy. You may have called it the first law of thermodynamics, but it's the same thing. The energy at the top equals the energy at the bottom. How many people remember this a little bit from Science 10? Okay, good. Now, you don't have to spot this little shortcut, but there is a little bit of a shortcut at this point. Anybody know what I'm talking about? Jordan? Yeah. You can get rid of m because it appears in every term. Right? If you divide every term by m, it cancels out. You don't have to do that. You want to put in the m there, the 500 grams. That's fine. It'll still give you the same answer. It just means a little bit more work on your calculator, that's all. G is 9.81. HI is 35 meters. VI was 5 meters per second. Now, what direction was that 5 meters? Downward? Should we make it negative? Lucas, should we make that a negative 5? No, we shouldn't. Why not? It's thrown downward, though. What's V stand for there, Shanta? Yeah, kinetic energy is speed, not velocity, right? If we're doing, say, D is equal to VIT plus 1/2 AT squared, we'd want to make it negative because V is a vector in that case, but here it's a scalar. Okay, a little bit tricky to rearrange, so let's do this as a group here. Let's do it one step at a time at 9.81 times 35. 343.35. Half of 5 squared is 12.5. Let's combine those now. Gives me 355.85 on the left side. Going to take over the half now. How are we going to do that? Jared, how do you want to take over the half? How do you want to get rid of it on the right side? Yep, you can divide by half. Or, what's the alternative for that? You can multiply by 2, either one. Okay, when you do that, you're going to get 711.7 equals V squared. And then, of course, you're going to square root that, right? $26.7 was it? And that should be 3 digits, right? 26.7 meters per second. You could have solved this using VF squared is equal to VI squared plus 2AD, right? You could have. But in the end, I want you to see that there is another way now. Okay, just a little aside here. Let's say we had have used VF squared is equal to VI squared plus 2AD. Okay, you could have done that on day 9 of class. Let's take a look at this for a second. In this problem, what's VI? 5 meters per second. VF, we just solved for. A is negative 9.81. D is the height, right? Let's take this. GHI plus 1/2 VI squared equals 1/2 VF squared. Let's do some things to it. Let's multiply everything by 2. See what I've done there? Now let's rearrange that a little bit. What do you end up with? VF squared equals VI squared plus 2GH. Doesn't that look an awful lot like that equation that we learned about 5 days into Physics 20? VF squared is equal to VI squared plus 2G or A, D or H. So really what we're doing now is the same thing as what we were doing. We're just doing it on more fundamental principles now, that's all. Right? Question? No? We're good there? Take a look at your worksheet number 5, please, your energy worksheet, conservation of energy. And I'd like you to take a look at the first 3 questions. Questions 1 to 3 on that worksheet. And then spend, I don't know, maybe 10 minutes of that. See what you can do, and then we'll do another example in class here, okay? All right, guys, we had 3 questions that we were working on just now, 1, 2, and 3. I want to do I want to do a couple of them. Which ones do you want to do? 1, 2, 3? 2? 2 and 3. Okay, 2 and 3 it is. 2 says a ball is dropped from a 60-meter high building. How fast is it moving when it's fallen halfway to the ground? When it's dropped, that means it's not thrown, right? That means that it doesn't have an initial velocity. So answer this question for me, please. What kind of energy does this ball have at the top of the building? It's not moving because it's not thrown, it's dropped. What kind of energy does it have when it's at the top of the building? Joseph, you look like you're just ready to give me an answer there. It's got just potential. So let's identify that. Let's say at the top, it's got just potential, and that's gravitational potential energy, right? Now, at the bottom, you know what, let's not label it bottom, because it's not at the bottom, right? It's halfway down. What happens to this ball as it falls from the top towards the bottom? What happens to it? This is not a hard question. What happens to the ball as it goes from the top to the bottom? It speeds up, right? It speeds up. As it speeds up, Joseph said it gains kinetic energy. As it gains kinetic energy, it loses potential energy because the total energy has to remain the same. If you gain one, you got to lose another. Now, when it's all the way down to the bottom, then you'll have lost all of the potential and it'll be converted to entirely kinetic energy. But we're not looking at all the way down here. This question is, how fast is it moving when it's halfway down? What kind of energy do we have when it's halfway down? Do you have kinetic? Yes, because it's moving. You have EK. Do you have potential? Do you have potential when it's halfway down? Yes, because it still has potential to fall. Some of that potential has been converted to kinetic, but some of it still remains. So partway down, halfway down, you've got kinetic and potential energy. Let's do our EI equals EF thing, the law of conservation of mechanical energy. At the top, it's just potential, so it's mgh. At the bottom, it's kinetic and potential, so we're going to say it's 1/2 mv squared plus, I said at the bottom, really shouldn't be at the bottom, right? Halfway down, it's got kinetic and potential. Now, once again, mass appears in every term, so I can cancel that. I get 9.81 times the initial height of 60 meters equals 1/2 VF squared, that's what I'm looking for, plus 9.81 times, what's the final height? What's the height halfway down, Peyton? Good, it's 30 meters. 9.81 times 60, I think is 588 point something. Take 9.81 times 30 over the other side by subtracting, and I'm going to end up with, on the left side, 294.3 equals 1/2 VF squared. Right, 9.81 times 60 minus 9.81 times 30 gives me 294.3. Divide that by 1/2, 588.6. Square root that, and we're going to get somewhere in the range of 23, 24-ish. What is it exactly? 24.26. We should round that to 3 digits, so we're going to say 24.3 meters per second. Yep. Yep. Oh, okay, interesting. And you got the right answer. Okay, let's take a look for a second at what Terry did, okay? Whether she did this on purpose or not, I'm not sure, but it works out, and it would work out every time. It's not a coincidence that it works out. Terry said, basically, once again, for number 2, EI is equal to EF, and she said, basically, paraphrasing a little bit, but she said MGH initial equals 1/2 MVF final. So she left off the potential at the end. She cancels this out. She gets 9.81 for G. What did she say HI was? She said it was 30. And what did she end up getting there? She got VF is equal to 24.3 meters per second. Why did it work out? Remember the day we introduced potential energy? We said it's always relative to something, relative to whatever you want. I made it relative to the ground, Terry. You made it relative to halfway down. Okay, so if this is, let's draw a little picture here. Here's the top. Okay, here's halfway down. Here's the ground. I said EP is equal to 0 here. Therefore, if that was the case, then my height halfway down is 30 meters, and my height when I started was 60 meters. What you did is said, this is my frame of reference. So therefore, your initial height was 0, sorry, your final height was 0, and your initial height wasn't 60, but rather it was 30, because you did it relative to that spot. Does that make sense? You can choose your reference point wherever you want. You chose it as being right here, halfway down on both sides. I chose it as being the bottom on both sides. It's not a coincidence that we got the same answer, though. Okay, I could have chosen it to be right here. Wouldn't make much sense to do that, but I could have done that as long as I was consistent on both sides. You got that? Okay, number 3. Number 3 says a 2.5 kilogram rock is thrown straight downward from the top of a building. How fast is it moving when it's fallen 10 meters? Oh, it's thrown straight down. I should have given you the speed at which it was thrown, right? Did you guys just assume that it was dropped? Like VI is 0? Did you guys assume that? Yes. Pretty much what you had to assume in this question, right? Because it didn't give you how fast it was thrown. Let's do it both ways. If it's thrown downward, then it's got potential energy at the top and kinetic energy at the top. When it's fallen 10 meters, how fast is it moving? Does it have potential? Good question. Has it reached the ground? We don't know. How high was the building to start with? 100 meters, 10 meters, 1,000 meters? We don't know. Terry, we're going to do what you kind of did in the last one. We're going to say, look, it falls 10 meters. Where's the ground? Who knows? Let's define this as our ground. Okay, let's make everything relative to this. If that's the case, then the initial height would be 10. The initial speed would be whatever you were given. Okay, and then the final speed would be the speed that it was moving when it reached that point. Does that make sense? Now, if you assume that it just was dropped because I didn't give you the initial speed, then we'd say EI is equal to EF. Once again, we'd assume that 10 meters down was our 0 point. Everything was defined relative to that. But this time there would be no kinetic energy at the beginning. In both cases, we could cancel out mass, and we're good to go. Let me give you one more example, kind of question that we're going to see on our field trip next month. Almost exactly like this, actually. I'll draw this one. Let's say we've got a roller coaster that has an initial height of 50 meters. Hey, do you guys know why? This is one of the questions on your field trip assignment, by the way. Why is the first hill of the roller coaster always the biggest? Why is the first hill of the roller coaster always the highest? Sam? Yeah, I don't like the word momentum. You guys haven't learned that yet. That's a Physics 30 word. Let's talk about it in terms of words that we've learned in Physics 20. Why does the first hill have to be the highest? Yeah, acceleration, yeah, sure. Something bigger than that, though. Yeah, sure. Yeah, in the end, you can't create energy, right? So whatever energy you have at the beginning, you're never going to have more than that. So if you want to go to a certain height later on in the ride, you better have at least that much energy to begin with at the beginning of the ride. Does that make sense? Okay. Get all the energy that you can get at the beginning of the ride so that you've got enough to get you through the ride in. So let's say we start off right here, 50 meters high, which is, by the way, the initial height of the Mindbender that you're gonna ride here in a month. 50 meters in the air. You know how long it's going to take you to go down to ground level? About 3 seconds. You're going to fall 50 meters in about 3 seconds. It's basically free fall. You're basically going to be weightless for those 3 seconds. Let's say we start off with a speed of 7.0 meters per second right there. And let's say we go down this hill, down to ground level, and then we go up here, and then we go up here again. Oh, let's do this even better. I want to know how fast that car is moving when it's upside down on this loop here, 25 meters above the ground. This doesn't look anything like the problem we just did where we dropped a ball from the top of a building, right? But it's exactly like it. We know that the energy doesn't change. We know that the energy rate here is the same as the energy rate here. In fact, we know it's the same as the energy here, 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 and here as well. The energy doesn't change. The total energy always remains constant if we account for everything. Let's make this our initial point. Let's make this our final point. And let's say EI equals EF. What kind of energy do we have at the beginning of this problem? When we're at the top of the hill, starting off, moving at 7 meters per second, what kind of energy do we have? Good. You got potential energy because you got a height of 50 meters. You got a lot of potential energy. That's why we have the highest hill at the beginning, right? So that we can maximize the potential energy, the potential to do something. And we got kinetic as well because we're moving, albeit pretty slow, but we're still moving. What kind of energy do we have at the final point, at the top of this upside down loop? What kind do we get there, Ty? Good, because you got a height. Anything else? Yeah, because you're still moving, right? I don't know how many of you guys have ever ridden a roller coaster where you go upside down. Okay, but if you have, you know that you don't stop when you're upside down. You've got to keep moving, right? So you've got potential and kinetic at that point. This should have been initial, by the way, right? 1/2 mvi squared. Okay, masses cancel again because it appears in every term. Now, Terry, the way you did that first question, you would have made HI 25 meters because you started from the bottom point, right? I'm going to make it 50. It doesn't matter as long as we're consistent. The final height would be 25. If you're Terry, the final height would have been 0. Now it looks a little ugly here. Let's do this here. 9.81 times 50 is 490.5. 7 squared is 49 times a half is 24.5. 25 times 9.81 is, help me out with that one, 24.5. 5? I don't know. $245.25. 490.5 plus 24.5 gives me 515. Take that over by subtracting. 269.75. Take the half over by dividing, about 569.5. Or 539.5 we'll go with then, sure. If you like that better, because it's right. And we square root that, and it's going to give me 23. What is it? 23 point. If we're going to round that, I should do 2 digits, so 23 meters per second. Guys, that make sense? Hey, what I want you to notice here is this. I could have rephrased this question. I could have not put in the diagram. I could have said, throw a rock from a height of 50 meters at a speed of 7 meters per second straight down. How fast is it moving when it's halfway down? Exact same question. It doesn't matter how the roller coaster got to this point. It doesn't matter whether it went down, took the path that it did, or whether it went down like this, went up and around another loop. Whoa, some crazy loops right there, like this. It doesn't matter how it got there. Bottom line is the energy rate here is the same as the energy rate here, regardless of what happened in between. Does that make sense? Good? Okay, I'm going to leave you with one question to do for homework tonight. We're done. Okay, just one question to do is practice. We'll take a look at it tomorrow, and then we'll do some review tomorrow in preparation for our test on Wednesday. A number of years ago, about 15 years ago, I was in Las Vegas. And they don't have this roller coaster in Vegas now, but they used to, way down the strip. It was at a place called the NASCAR Cafe. You would start inside this building on the roller coaster, horizontal, and then they would shoot you out like with this electromagnetic propulsion system. Like, you ever been to Disneyland and California Adventure, the roller coaster they have there where they fire you going and then up this hill? It was like that. They'd fire you out the building, around a turn, down a little hill, and then you'd go straight up. And then you'd slow down, and then all of a sudden, the track was gone. The track stopped. There was no track. You would come up to the end of this track, approaching the end of this track, as you start getting scared because there is no track anymore. But just before you got to the end of the track, miraculously, you would stop, and then you would go back down through the whole thing backwards. Let's say that we start off at a height of 10 meters. Let's say that we start off with a speed of 20 meters per second, because in that roller coaster, you had to be going pretty fast before you started going up this hill. My question is, how high up the hill will you go before you stop? What kind of energy do we have at the beginning of this problem? What kind do we have at the beginning? Is it moving? Kinetic. Is it potential? Yeah, because we got a height. What kind do we have at the end of the problem? Over on the right-hand side. Goes up, goes up, goes up, goes up, goes up. At maximum height, it kind of we have at the end. Just potential, right? Got it? See what you can do with that, and we'll take a look at it tomorrow.